We have already derived the expression for an ideal gas of volume in terms of the initial volume, initial and final temperature, initial and final pressure, times the effect of conversion. If you remember, epsilon was the initial mole fraction of A, YA0, times delta. Delta was the net stoichiometric coefficient. Now let us write the mole balance species conservation equation for a batch reactor. This is R sub A times V, and now we are going to substitute this term for V. This is going to be RA times V0, T over T0, P0 over P, times 1 plus epsilon x. But let's treat the whole system together. Remember that we were writing Ca as an A over V. Let us derive our expression for concentration instead, because we will need concentration in RA as well. So this is equal to Na0 times 1 minus x divided by this V. V0 T over T0, P0 over P, times 1 plus epsilon x. This term is Ca0. Ca is equal to Ca0 times 1 minus x divided by 1 plus epsilon x times T0 over T times P over P0. As we advance, we will incorporate the temperature into this equation through the equation of energy, and pressure into this equation through the equation of momentum. Conservation of momentum and conservation of energy have to be simultaneously incorporated. All right, now for an isothermal reactor where pressure does not change significantly, we can simplify this expression into Ca is equal to Ca0 1 minus x divided by 1 plus epsilon x for the conditions T0 over T is approximately 1 and P0 over P is approximately 1. And if there is no volume change, In other words, if there is a zero stoichiometric coefficient, epsilon term will disappear, and our CA is going to be CA0, 1 minus x. And we are going to solve the species conservation equation by taking the epsilon into consideration.